All right, looking at some more related rates problems. And these are all problems that are going to involve angles on some level. I've got three problems we're going to look at. Here's the first one. We have an aircraft climbing at a 30-degree angle. So our airplane here is represented by the black line, and it's climbing at a 30-degree angle, and that's fixed. So I can go ahead and label the angle 30. We'll see the airplane is traveling at a speed of 500 miles per hour in this direction right here. So maybe I could draw an airplane. Should I draw an airplane? Here's an airplane. Oh, it's green, a green airplane. There we go. There's my airplane. Let's give it the tail. There. Okay, so there's our airplane. He's traveling at 500 miles per hour. Now that's a rate of change. Something is moving at 500 miles an hour. So I've got to figure out what is it that is changing at that speed, and that would be the hypotenuse. If the plane is moving in this direction, then this length right here, which I'm going to call P for plane, is increasing at 500 miles per hour. So I have some rate for the plane, and we want to know how fast is the aircraft gaining altitude. So here's the altitude, the distance from the plane to the ground. That's our red dotted line, and I'll call that A for altitude. And we're ultimately trying to figure out what is dA dt. I didn't give you as much information on this one as I usually do. Usually there's more information in a related rates problem than this, but this is what we have to work with. We have the fixed 30-degree angle. And now, as with every other related rates problem, we've got to find some way to tie together the variables P and A. And so there's a couple ways you can do this. Probably the easiest to understand would be to go into your old SOHCAHTOA right triangle trigonometry. Because if you look, we have a given angle of 30, and we have the opposite side and the hypotenuse, which means we're going to be doing the SOH. So I would say sine of 30 degrees is opposite over hypotenuse. The sine of 30 degrees, that's unit circle stuff, is not 1/3, it would be 1/2. Is A over P. And then I could cross multiply that and say that P is equal to 2A. And that's true. P is the same thing as 2A. And we just proved that by using trig. You could also remember your special case right triangles. This is a 30, 60, 90 right triangle. And if you remember the ratio, the short leg is always half of the hypotenuse, or the hypotenuse is always twice the short leg. It didn't come into play, or at least it hasn't yet, but the long leg is the short leg times the square root of 3 as well. But we have an equation, P equals 2A, and we finally have that. We could take the derivative of that. We're trying to find dA dt. That's our goal over here. So since I have an equation, I can now do the derivative. The derivative of P is going to be dP. The derivative of 2A is going to be 2 dA dt. And now we can just plug in. dP dt is 500 equals 2 dA dt. And then we could divide by 2, and we'll get 250 equals dA dt. And always, 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 always remember to put in your units. So we have to think altitude would be a measure in miles, and it's per time. So this is going to be miles per hour. So there's our answer. dA dt is 250 miles per hour. Good, good? Good, good? All right, let's move on to the next one. They're going to get slowly more difficult. For this problem, the camera is mounted 3,000 feet from the base of a rocket launching pad. So this problem, well, we have the red line represents a rocket. I'll draw a better rocket. A rocket. Now, that was supposed to be a rocket. Now it's just a red blob. That was a terrible idea. What am I thinking? So this is a rocket, and our rocket is taking off vertically, and rockets do tend to take off vertically. And we have a camera right here. So here's some camera. Draw some old-fashioned box camera. Y'all remember these? Probably not. You have the little cranky thing that you crank. So we're tracking the launch of this rocket, and the camera angle is going to have to change. As the rocket rises, the camera will have to change its angle in order to keep track of the rocket. And the question here is saying, when the rocket is 4,000 feet above the ground, how fast is that angle changing in order to keep, so the camera can keep track of the rocket? So let's see, our given information, the camera is 3,000 feet from the base of a rocket launching pad. That would be this distance. And I don't think that's going to change. The camera is stationary, the launching pad is stationary. That is 3,000 feet, and that's constant. I can go ahead and label that with the distance. The rocket launches and rises at 800 feet per second. Okay, 800 feet per second is a rate, and I'll just call this R for rocket. So we know that the rocket is rising. That length is going to change at 880 feet per second. Then we are looking at a point in time when the rocket is 4,000 feet above the pad. Now that's not always true. That's going to change. So I'm not going to label this 4,000 just yet. But I will make a note that we are looking at a point in time when R is going to be 4,000. I'm going to put a little flashy thing around that to remind me not to plug it in yet. Let's see, how fast must the camera angle change to stay fixed on the rocket? Okay, so there's all of our information. We've got to come up with some formula to tie theta in with R, and we are looking for the rate the angle changes. So I guess I need to make note that my end goal is to find d theta dt. Whoops, d theta dt. And so we've got to come up with some kind of an equation. So I'm looking at this. I have an angle, and whenever you're dealing with angles, you're almost always going to be dealing with some trig function. So I have theta, I have the opposite, and I have the adjacent. And the adjacent is fixed. If you have the option of using a fixed side length, always do that because it makes derivatives a lot easier. Well, opposite and adjacent, that's tangent. So my formula is going to be the tangent of theta is equal to opposite R over adjacent, 3,000. And then we're going to take the derivative of that. Derivative of tangent is secant squared times secant squared theta, but then we have to multiply by d theta dt. And the derivative of R over 3,000 is going to be 1 over 3,000. Please don't use quotient rule for that. dr dt. And now we start trying to plug in. And you're going to run into a little bit of a problem here. D theta dt is the unknown, so that's going to remain d theta dt. 1 over 3,000 is already given. dr dt, okay, that was given. That's 800, so I can go ahead and plug in, not 800, but 880. I can go ahead and plug in 880 for dr dt, and I'm always keeping note. I don't write the units in here, but just be aware of the units. Now, secant squared of theta. The first time people do these problems, they pull out their calculator and they say, well, if R is 4,000 for some point in time, we could actually find the angle theta by doing the inverse tangent of 4,000 over 3,000, and you could get an angle for theta that way, but you should be able to do these problems without a calculator. I'm not going to expect you to find theta. So we're going to have to go a different route to get secant squared theta. And what we're going to do is still using right triangle trig. This is a 3, 4, 5 right triangle. It's just everything is multiplied by 1,000. So my hypotenuse I know is 4,000. Well, secant squared theta, let's go into thinking land for just a minute. Secant squared theta is the same thing as secant theta quantity squared. And if you think about secant, secant is the reciprocal of cosine. Let's see, cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So if I want the secant of theta, I don't need to know the measure of theta. All I need to know is the ratio of the side lengths, hypotenuse over adjacent. And in this case, hypotenuse over adjacent is 5,000 over 3,000. Or that would reduce to simply 5/3. So secant squared theta is simply 5/3 squared. We don't have to find the angle. You simply go old-fashioned right triangle trig. Using SOHCAHTOA, Old Henry always has old apples, whatever mnemonic device you want to use. So at that point, we now have all of our stuff plugged in. We have 5/3 squared. Let's clean that up. That's what, 25/9 d theta dt. Now, I'm usually not a big fan of cleaning up, but I could at least cancel one of those zeros, right? So this would equal 88 over 300. And then d theta dt is going to be 88 over 300 times 9/25. And I realize that would clean up, but you know what? I'm not going to worry about it because that's arithmetic, and I'm more interested in you understanding the calculus. So we get d theta dt is 88 times 9/25. Always remember your units, and angles are always measured with radians. So this unit is going to be radians per, and I think we're doing hour or second, feet per second. So radians per second. So there's our unit for the rate the angle changes. Good, good? Good, good? Good, good? All right, one last problem. A rotating spotlight makes a revolution every 10 seconds. Is located on a ship 4 kilometers from nearest point of straight shoreline. How fast does the spotlight move along the beam when it makes it? Okay, so let's try to draw this picture. We have a ship anchored off the shore. We have a straight shoreline, which makes this problem a lot easier. So we'll call that the shore. This side is land. And we have a boat sitting out here in the water. So here's our boat. Hey, give me a sail. So there's our boat. And our boat has a light on it. So here's a light, and the light is revolving. The light's going in circles. So let's draw a light. Let's get a yellow light. I think that'd be a great idea. Let's do that yellow. Now, let's see what that one. So we have a light, and what's happening, can y'all see that? That may have been a bad idea. I'll tell you what. We'll just stick with solid stuff. Sorry, I'm killing time now. I didn't plan this out too well. All right, so we have a light, and the light is going in a circle like this. So it's like a rotating light. It's a little spotlight, and it's making 1 revolution every 10 seconds. So it's actually going kind of slow. It's going slow. It's making 1 revolution every 10 seconds. And the light's going to hit the shore and then travel along the shoreline, travel along the shoreline, travel along the shoreline, and then come back out to the ocean, hit the shore, travel, travel, travel. And what we're trying to figure out is when it makes an angle of 45 degrees with the shoreline. So about right in there. When it makes an angle of 45 degrees with the shoreline, how fast is this point moving along the shoreline? That's what we're looking for. So this is going to be triangles. We do know that the boat is anchored 4 kilometers from the shoreline. So this distance right here is 4 kilometers. And that's fixed. The boat's not floating anywhere. We're going to stay right there. That's going to be a right angle. We measure with perpendicular to the shoreline. Let's see, what other unknowns do we have? We have some angle that's changing, right? This angle, because the light is rotating, this angle is changing. So I'm going to just call that theta. Let's see, we want to know how fast the beam is moving across the shoreline. Well, if this point is moving to the left here, then this distance right here will be shrinking. That's the distance that's changing, and that's actually what we're trying to find. What is dx dt? That is going to be the distance we're trying to figure out the rate of change. Let's see. Rotating spotlight makes 1 revolution every 10 seconds. 1 revolution every 10 seconds. That sounds like a rate. They're telling you how fast this thing is spinning around, which is going to be related to the rate of the angle. So the angle changes at 1 revolution for every 10 seconds. Okay, the problem with 1 revolution every 10 seconds is a revolution is a very bizarre unit of measure. We can't do revolutions. We have to change that since we are dealing with angles. We have to find a way to convert that into radians. And you think 1 revolution, if we go in a full circle, 1 revolution is going to equal 2 pi radians. So my d theta dt is going to be, the revolutions cancel, the 2 over 10 cancels, and it's simply pi over 5 radians per second. So now I have a rate that the angle changes. The angle changes at pi over 5 radians per second. Let's see, let's keep going here. If it's looking at a point in time when this angle is 45, so we're looking at a point in time when that angle is 45, now that's going to change. But if that angle is 45, then theta would also be 45. So we're looking at a point in time when angle theta is 45. Not always true, but true for a split second. And if theta is 45, then we have an isosceles triangle, so I know that x would also be 4, because it's going to be the same length as the distance from the shoreline. So x is also going to be 4. And we are looking for dx dt. Let's come up with some kind of a formula. What kind of equation could I come up with? I have an angle. These two sides, 4 is fixed, so I want to use 4. I think tangent's my best bet again. Tangent x over 4. Then I could go ahead and do the derivative. The derivative of tangent is secant squared d theta dt. The derivative of x over 4 is 1/4 dx dt. And then we'll start plugging in. Secant, to get secant, what did we say secant was? I know cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. The hypotenuse, we can figure that out because we know that x is also 4. Hypotenuse is going to end up being 4 square root of 2. So hypotenuse over the adjacent side is going to be 4 root 2 over 4. We're going to square that. D theta dt we figured out was pi over 5 equals 1/4 dx dt. And we can solve that equation for dx, and we'll be done. I'm going to go a little bit crazy here. I usually don't simplify, but those 4's cancel. Square root of 2 squared is 2, so I have 2 pi over 5. And we're pretty smart. I'm going to go ahead and multiply by 4 also. Is that okay? I'm going to go ahead and multiply by 4 to finish solving for dx dt. And that would give me a final answer of 8 pi over 5 equals dx dt. And now we just have to figure out the units for dx. X was a unit of distance, so we go back and look and see what kind of distance measures we've been using. We have kilometers, and time is measured in seconds. So my answer is 8 pi kilometers per second. And there we go. That took a little bit longer than I thought, but I also bumbled my way around drawing the picture. So there's some related rates with angles, and we'll hammer these home in class.